Let's get started. Today is sadly the last day of the bootcamp, but you know, at the end we have the best. Today's session is kicked off by Stefanie Jegelka from MIT, who I have a pleasure to have as a colleague, and she will talk about connections between submodular optimization, which is a very discrete topic, and first-order methods of continuous optimization.
Okay, thank you. So this is lecture 3 in the series on continuous methods on discrete optimization. And since submodular optimization is a very rich topic to show sort of interactions between continuous and discrete optimization in various different ways, so let me just show you a bunch of examples sort of in this topic, how you can actually take this discrete optimization problem and transform it to a continuous optimization problem, and actually also vice versa. Obviously there has been a lot of work on submodularity and optimization, and we have lots of experts also here in this workshop. So my goal here is not to give you sort of a laundry list of all the best possible results and bounds you can get, but more sort of convey some of the main ideas, how you get to some of these results and how you. And again, if you have any questions, please ask. If I'm going too fast or too slow, please let me know. Okay, so let's get started. So first of all, what is a submodular function? Submodularity can actually be defined pretty broadly, but let's start with the notion of a set function and submodular set function. So set function means we have a discrete collection of items that we call the ground set V, and we can take subsets S of these items, and we have a set function that assigns values to all of these items. So that's our set function. And we will want to maximize or minimize this function depending on whether this is a cost function or a probability or utility function or something like that. So now in general, this can be a very hard problem. Any of your favorite NP-hard problems you can probably phrase in this way and then say you want to minimize or maximize such a function. So we need some properties that make it a bit nicer. So one such property is submodularity. What is submodularity? There's basically two ways to define it here. The maybe more intuitive way is via diminishing returns. So diminishing returns means the following, that I have already selected a set S, and I see how much does my function increase when I add one more item to A to my set. So this is the marginal gain. And as my set S grows, so if I take a larger set and I add the same item A, the marginal gain can never increase. So basically, the more I know, the less I gain from one more item of information. Or if I already have a cap, maybe getting one additional cap is actually not so valuable. But if I don't have any, then this one cap is actually very valuable to me. So you can think of it that way. It also models economies of scale. If you think about typically producing larger amount is cheaper on average than producing smaller amounts and so on. So this is why these functions have also been important in economics. Okay, I already wrote this same definition over there because we will need it over and over again. So this is diminishing returns or diminishing marginal gains. Okay, so that's one way to define it, and I think it's pretty intuitive. You maybe already see that several problems may have this kind of property. There's an alternative way of defining submodularity that's actually equivalent, and we will need both of these, so I'm showing you both. The second one is, here we say, okay, S has to be a subset of T, and we sort of look at these marginal gains. And in fact, you can think of these marginal gains also as a discrete derivative. So if you think of this as a discrete derivative, this is a bit like, as my set grows, my derivative should shrink. So it's a little bit like concavity in a discrete sense. So here's the other definition. Other definition says I take two arbitrary sets, A and B. And if I evaluate f at A and f at B, that should be larger or equal than f at A union B plus f at A intersect B. So these are equivalent, I'm claiming. So to see that they are equivalent, you just have to do some rearrangements. So one direction you can prove as follows. You say A is the same as S union A, B is the same as T. And then you just know that the union of the two will be that large set with T union A, and the intersection will be S. And you see by rearrangement, this implies this. The other direction you can prove by induction. So this is actually fairly straightforward. Yes?
Are these the only restrictions on F, or do we require like non-negativity or something?
Right now, we don't need non-negativity. And they actually can be positive and negative. When we may need it later on when we talk about maximization. Right now, this works for anything, essentially. Okay, let me just write down this also so that we can remember it. You don't need to keep it in the head. So for all sets A and B, we need that f of A plus f of B is bigger than. So far, so good. So we have the definition, but why do we care about these functions? And to give you a little bit of intuition, let me take a quote from a paper from the 18th. This was a seminal paper by Lovász, where he looked at relations between submodular functions and convexity. So first he argued, why do we care about convex functions? Why are convex functions so important? Well, in pretty much everywhere. And he says, well, there's basically a few different points. One is they occur in many models in economy, engineering, and other sciences. And they are often the only non-trivial property that can be stated in general. So pretty much like very generic, it's widely applicable. Second, you can do many transformations, so they are preserved under many operations and transformations. So that gives you a larger effective range of results. If you prove something for a convex function, you can transform it, you can derive others, it's going to still hold. The third one is they still have, so they are widely applicable, and they have a sufficient structure for a mathematically beautiful and practically useful theory. And the fourth one is you can do efficient minimization. So some of these are more conceptual, and some are actually also like more actually a bit more mathematical points. And then he goes on and he says, well, it is less apparent, but we claim and hope to prove to a certain extent that a similar role is played in discrete optimization by submodular set functions. So this is more of his conceptual connection, but in this paper actually he goes on and he makes some more formal connections too. And in fact, it's true that the last point holds, and there's actually very crisp formal connections also between submodularity and convexity, as we will see. So that was in this paper. We will get back to this paper over and over again. So before we get to that, those connections in a bit more detail, let me show you something about the first point. So what are some examples of functions that actually have this submodularity property, just briefly? So obviously linear functions. If you have just every item has a weight and you sum up the weights of the items that you pick, that's a linear function that satisfies all these inequalities over there with equality. Very simple example. But there's others, more interesting examples. Maybe, so for example, entropy of discrete random variables. If you take the ground set to be a collection of random variables, and as the function you take the joint entropy of these variables, that's going to be a submodular function. And similarly, mutual information. Then some other examples is if your items are actually vectors and you pick these items and you put them together in a matrix and you measure the rank. So matrix rank functions, that's going to be a submodular function. And also more combinatorial generalizations thereof. So matroid rank functions, Michel had mentioned matroids. So they also have something like a rank, they have rank functions, if you know what they are. And these also satisfy submodularity. So think of them as a combinatorial generalization of rank. Then functions like coverage functions. So max cover is a submodular maximization problem. You can see very easily that coverage functions, where I select maybe some sets and that covers some area or some other items, that's going to have the diminishing returns property. The more I've already covered, the less I gain from choosing more sets. And very similarly, actually, diffusion in networks. So if I pick some seed nodes in a network and I see how does maybe information spread, and I look at what sort of the area or the nodes that I've covered in expectation is like a randomized cover, also has submodularity property. Volume functions that are defined by determinants, and also an important one, graph cuts. So minimum cut problem is the submodular minimization problem, where here we are picking nodes in a graph and we are measuring the edges that we have to cut to select these nodes. Okay, that's just a few applications. I'm not going to talk much about like more applications or instances of these. I'm going to talk more about sort of optimization. Okay, so what am I going to talk about today? So first of all, I'm going to show you how do these submodular functions connect to continuous optimization, how we can exploit continuous optimization to do submodular optimization. And then, in the end, I will also talk a little bit more about the other direction, that actually there's also examples where you can do continuous optimization via discrete optimization, and looking at submodularity a bit more generally beyond set functions. But you see that many of these ideas will occur here again. And if we have time, I'll talk a little bit about other connections between submodularity and continuous functions and optimization. Okay, so let's start with optimizing a submodular function. So we have this discrete set function. It's a very discrete optimization problem. How do we optimize this function? And I just said optimize. There's two ways I may want to optimize it. I may want to minimize it or maximize it. And of course, this is very different. And I may need different methods for minimization or maximization. And some question that will actually become sort of a question that we will encounter throughout the talk as well. Is submodularity more like convexity or concavity? If you think about minimization, you would like this function to be as convex as possible because we know how to do convex minimization. But convex maximization is not so easy. So if we actually want to maximize it, we would rather want this function to be as concave as possible. So that's like how we will use it. And in fact, there has been a debate about this. So I showed you that paper by Lovász. In that same paper, he actually also shows connections to concavity and argues that actually submodular functions also have very close connections to concavity. And I already hinted at something. If you look at the diminishing returns, that's like discrete concavity. And in fact, if you define a set function in a way that you say, I take the cardinality of the set and I take a scalar function of that cardinality, that thing is submodular if and only if that scalar function is concave. So there's close connections also to concavity. But there's also close connections to convexity too. So I hinted at it, and actually, to give you one more hint, if you look at this inequality, and if you know the definition of midpoint convexity, and you sort of view these two as some kind of average of your sets, then this is a little bit reminiscent of midpoint convexity. There's going to be a more formal connection too. And so Fujishige in a paper wrote this, that yeah, somehow submodular functions, that looks like discrete concavity, but if you look at duality results, they always somehow, the inequality is always in the wrong way for that. So they always occur on the wrong side. So in that sense, they are more like convex. And we'll get to that. And indeed, there's even a notion of discrete convexity, really, which generalizes submodularity that was studied by Murota. Okay, so much for the concavity-convexity relations, and we'll encounter these. So now let's say, how could we use continuous optimization for submodular optimization? So I'm talking about continuous methods, so let's look at continuous methods. The first thing to notice is that, well, we have the set function, but maybe for continuous relaxations or reformulations, it's more convenient to think about vectors than subsets. And obviously, there's a very close connection between vectors and subsets. We just take indicator vectors. So basically, for each item, I'll have a coordinate xi. If I pick that item, xi is 1, otherwise xi is 0. So I can equivalently write my function as a function of binary vectors. One-to-one correspondence is just the same. So now the question is, how could I take this problem and make it a continuous optimization problem? So, well, one way to do continuous optimization problem is to an LP relaxation. But so there's basically not an easy way to write this problem as some kind of C transpose X, because F is nonlinear. So it's very special cases linear, but mostly like if you have these strict diminishing returns, it's not going to be a linear function, so you're not easily going to get this out. You can do a linear programming relaxation. What you have to do is you pick one variable for each subset and basically use these as indicator variables. Say they have to sum up to 1, and then you just take the evaluations of the function as the coefficients. So you get a linear program out. It's a very simple linear program. It's exponential size. You can do it. And in fact, what we will do is very closely related. It's sort of, you can view it as a collapsed version of this, but let's look at something else than the linear programming relaxation. And that means, okay, we will have to do a nonlinear program. So what we will try to do is we will find a nonlinear function. So we will relax now this to the hypercube and find a function that we can evaluate on vectors that have entries between 0, 1, and that we can somehow optimize instead. And then somehow go back to the other side. So that's the plan. So how to do this? What could be this function? And let me just show you the picture, and let's see what we want from such a function. So here, basically, the thing is I have two items in 2D, so I have one dimension for each item, and if I have two items, there's 4 subsets I could pick. Nothing, A, B, or A and B together. So this will be 0, 0, 1, 0, 0, 1, or 1, 1. So my function can really be evaluated only on like the corners of the hypercube. So what would I want from this function little f? So for once, I would maybe want it to be somehow close to my discrete function. So maybe I would want it to coincide with my discrete function, at least on the discrete points, and otherwise be somehow close that if I have a solution on this side, I can somehow go back to a solution on this side and know I'm not losing too much. And the second thing is that this little function, little f, should somehow be easy to optimize. Otherwise, it's not so useful. So what could this function be? So if I just say I want an interpolation of these points that's somehow a continuous function, in fact, there's many different ways I could do this. Infinitely many ways, in fact. And the question is, which of these functions actually has these other properties that are useful for optimization and somehow useful for rounding in some way? And here it's the difference if I want to do minimization or maximization. So let's focus on minimization for the moment. So maybe I would want this to be somehow easy to minimize. So here's a generic construction how we could reach at such an extension or continuous function that interpolates our submodular function. So we know we can evaluate our submodular function on discrete vectors, and now I have a continuous vector, and I want a function that I can evaluate here that has something to do with that function. So one way to do it, and this is actually an old trick, is to say, well, I view these fractional entries here as probabilities. So I somehow say that this vector z here means that I choose A with probability 0.5, I choose B with probability 0.5, and D with probability 0.8. And then I say, okay, this gives me a probability distribution, and I'll take expectation under this distribution. That gives me a continuous function. So formally, what we will do is we will define a probability measure over subsets or over binary vectors such that the marginals agree with z. That means the probability that I is 1 equals ci. And then our extension is going to be the expectation under this probability. So that's going to be a continuous function. It's going to be defined on all the z's. And obviously, if z is binary, these probabilities will be deterministic, so I will actually coincide with my set function. So is this well defined? So it's well defined up to something, and the something is that, well, I said the marginals should agree with z. But what is the joint distribution? I can have many different joint distributions that have the same marginals. I haven't specified that yet. And depending on what is the joint distribution, I will get out different extensions here. So that is the important thing to notice. So, well, let's look at some joint distributions and see what comes out. So simplest joint distribution would be to say they're independent. That's the most straightforward thing to try, so let's try that. Which means that the probability of a certain set is exactly this. I flip a coin for each of these. That's the easiest one. So what happens with this one? The first thing that's easy to notice is this is actually going to be a polynomial in Z, a so-called multilinear polynomial. And it's also called the multilinear extension of the submodular function. Now, if we think about optimization, here's a picture in 2D. This is what it looks like in 2D for my example function. You see this is not really convex. It's not really concave. It looks a bit like a saddle point function here. So maybe if I would want this to be a relaxation for my minimization problem, this is going to cause some trouble if I actually want to minimize this guy. It's not useless. It's just right now not so useful for minimization. So what we actually would like is something that is looks like a convex function here. The question is, can we get this? With our definition, with these expectations, can we get something that's somehow nice and possibly convex and easy to minimize? And in fact, you can, but it's maybe not obvious. It's actually not obvious how you get to that. Let me just show you the construction and then argue why this should be something that has good properties. So here's the construction. Again, we have our marginals. We want the marginals to coincide, but this time we correlate the variables pretty much very strongly by what I call level sets. So here you can think of it this way, that you think of this as a histogram or mountains. So we have like 0.5 length here, we have 0.8 length here. And now we randomly draw a threshold between 0 and 1. And we pick all the items that exceed that threshold. So here I'm picking A, B, and D. So you see, actually, this correlates them a lot because I can always either pick them together or not pick them together. And in fact, there's only here, in this particular case, there's only 3 sets I can pick. Nothing, D, A, B, D, and if the C was bigger than 0, I could pick that also. That's it. Versus if I pick them independently, I can pretty much reach any set unless I have a 0 in there. That's a big difference. So in that sense, actually, that expectation is easier to compute. I have only at most n many sets that I can even sample, and I call these the level sets because you get them sort of, if you think of these as mountains, that's sort of the heights. If you cut your mountains at different heights. So these are the level sets, and this particular construction is also called the Choquet integral of the set function. So again, plus 0.1 is this is relatively easy to compute by just computing these levels that you can get by sorting. But what is not so obvious is, why should this have any good properties? Why is this useful for optimization? And in fact, it is not obvious because here, for example, this I can define for any set function. Actually, like the other one, I haven't used submodularity at all up till here. But this is a convex function if and only if the set function is a submodular function. So here is our close connection to convexity. This is the if and only if. If this is a convex function, the set function was a submodular function, and vice versa. And this is actually what it looks like in our picture. So now this looks like something that may be useful for optimization because it's convex, at least. So convex minimization I know how to do, and it's over a pretty simple set, so I may know how to do it. What is still maybe not so obvious is, why should this hold? Why would this be a convex function? So let me give you a little bit of an intuition why this, what is actually the connection that you can see that this should be a convex function, which would be sort of a hint on one direction. So to see this, let's take a closer look how you actually, what is the evaluation of this? So I said you have these level sets as you sort of take your threshold and you go through here. And in that expectation, you have to use each of them and use a combination of these with weights. So what's going to be that combination? So let's maybe do it here. So how to compute this is, if I take my vector z and I sort it from large to small entries. So I say I just renumbered the coordinates. So I say z1 is bigger than z2, and so on up to zn. So I sort it. And now what is this, this guy here? Basically, in that case, f of z is zn times the full set. That's basically when the threshold is sort of up until it hits the first of these, the smallest of my entries. And then what's the next time my set change is basically when I hit the next of my values, and so on up to z1 minus z2 f of s1. So roughly, this is what this expectation is going to look like. These are all non-negative because I have sorted them. Sorry. And it's a non-negative combination of my function values. So I can actually also write this as an inner product of my vector z with some vector s that depends on some evaluations of the function, my function at different sets, or actually differences of these evaluations, just by looking at the evaluation. Okay, so why does this show convexity? And in fact, here's why this actually shows convexity. If my function is submodular, this little vector s is actually exactly the same as the solution to an optimization problem, which is a maximization problem where z is the cost function and this s lives in a special polytope. So I'll say something about that. But what this means is that this f of z is actually equivalent to a pointwise maximum of linear functions. And a pointwise maximum of linear functions is convex. And you see, actually, it's also a piecewise linear function, and that's exactly what this looks like. So this shows it's convex. How you prove this is by LP duality, by noticing that this is actually the optimal solution. So what is this guy here, this BF? This BF is a very special polytope. Every submodular function has a special polytope associated with it. And this polytope is defined by the submodular function. So it's defined, it's called the base polytope, and it's defined as the set of all vectors in Rn such that are essentially dominated by my submodular function. So for all subsets T of V, so basically I sum up all the items. I view this as a linear function and should be dominated by my submodular function. And the entire thing should sum up to submodular function evaluated at the full set. And you see it has actually exponentially many inequalities. These are defined by the f of t's or f of s's. And here basically we get the tight inequalities out. So that's why you get actually these f of s's are basically the right-hand sides here. The amazing thing is that this is a polytope that has exponentially many inequalities, all of which can be valid. But you can do very easy optimization over this polytope, as you see. You just need to do sorting, and that's it. So n log n, and you're done. And you have seen special instances of these polytopes. So examples are the probability simplex, so-called permutahedron, the spanning tree polytope, any kind of matroid polytope. And so they all have this property. Actually, they all are instances of these base polytopes. And this specific fact that you can do this linear optimization over the base polytope in n log n time, or polynomial time, essentially underlies essentially all the tractability of submodular minimization. We can do this. We can compute this. That means we can compute this, and this has many other implications. Okay, so this is a very important insight. Now we have an extension that's convex. Can we use it for optimization? So one thing we might want to do if we do optimization is, well, if you think about it, simplest optimization thing is run a gradient descent method, or in this case, subgradient method, because this is not differentiable. We need to be able to compute the subgradient. What is the subgradient of this function? It's not obvious from the expectation, but it's obvious from here. You compute the argmax, that's going to be your subgradient. So it's easy to do. We know how to do it. So it's easy to compute the subgradient. That means we can do, at the very least, a subgradient optimization. Projected subgradient method or something like that. Very first thing we could do here. So we can optimize this function, and we can do something smarter than subgradient method, but we can do that. The second question is, if we have minimized this function, how do we get back to a discrete solution? Because that's what we actually want. Yes?
Is Is there a converse to this theorem of Lovász that if you start from some base polytope, then you can construct some submodular function?
Yeah, so if it's a submodular, if it is basically a base polytope, you will get a submodular function out. So you can actually define your submodular function via this polytope by saying I have a function where this is a binary vector, and I define a function that's exactly defined like this for binary vectors, so you get a set function out. That is submodular only if this has essentially the base polytope properties.
Which means that it's a matroid polytope?
Yeah, so if it's a matroid polytope, this is going to be submodular.
It's a matroid intersection polytope?
That's not a that's not going to be a submodular function. That also you cannot do greedy optimization over. So matroid intersection, or like even more matroids, it's not going to be optimal if you do just a greedy simple algorithm by sorting. So this is actually, this greedy optimization is very closely related to the base polytope properties. Good question though. So what about rounding? So let's say we have the optimal solution Z star. How do we get to a discrete solution? And now actually we can realize that what would be little f of Z star? It's actually just a combination of function evaluations with non-negative coefficients. So if this guy is the minimum, one of these level sets at least has to be the minimum, or actually all of them. So we can, if we have an optimal solution Z star, we basically just look at these level sets. So we do threshold rounding essentially and find the best level set. In fact, you can take all the entries that have value bigger than 0. That's going to give you a minimum. So rounding is super easy. Optimization is relatively easy. At least we can do a subgradient. So we actually have an exact convex relaxation for this optimization problem. So we have a way to take our fairly complex submodular function and transform it into a convex optimization problem where we know how to round it back to an optimal discrete solution if we know how to do this. And this now is a convex optimization problem where we know how to get a subgradient. It's over a very simple convex set. So now we can take all what we have learned about convex optimization in this week and use anything we like that applies to this non-smooth optimization problem. So we can get many different algorithms out, yes?
So is this distribution the only distribution that leads to convex functions? The marginal result.
I'm not exactly sure, but this leads to what is called the convex envelope, which is the largest convex function that essentially fits underneath your function. So this is in some sense the closest convex function you can get. Any other question? Okay, so with this, let me just give you a very abbreviated overview of what you can do to now optimize this Lovász extension or do submodular minimization. The very first method that was applied here that actually proved that you can do submodular minimization in polynomial time was the ellipsoid method. Noticing when this came out that you can actually run the ellipsoid method, it was by far not a practical algorithm, but it proved polynomial time, which was a big thing and answered an open question at the time. Then, of course, another example is the subgradient method, as I pointed to, which will give you not exactly a polynomial time algorithm. So if you want, say, a gap of epsilon between the optimum and your solution, you need 1 over epsilon square iterations. But it's very easy to do this. And there's also improved versions with a stochastic subgradient methods, more recent ones. Yes?
I'm a little bit confused. Why is it that for V with the Z and in the evaluation of function, what you wrote on the board?
Here, yes?
Yes.
Oh, this is the full set. So this is basically Sn. So if you think about, say, you have this vector that gives you this histogram of like the different things. So you take your threshold. This is going to be S0 is going to be empty set. These are all the possible sets you can sample. So what you want is the expectation of f of s. What is the expectation of f of s? It's basically the sum over all subsets, the probability of the set times the f of s. What's the probability of achieving that set, sampling that set? So basically what this would be is sum over all subsets, probability of sampling that set times the function evaluated at this set. Right? This is just the definition of expectation. So the question is, what is this probability under the distribution we defined? So the distribution we defined was that we pick a random threshold between 0, 1, so here's 0, here's 1, uniformly at random, and we would, whichever, like if it hits this bar, we're going to pick only this item and so on.
Threshold, then it just hits all the...
Exactly, and if the threshold is small enough, it's going to hit all of them. And this is basically the smallest entry in my vector. So this is going to be that's why f of v.
The s on the third line is different from the s's on the previous line, right? So inner product z comma s.
Oh, yeah. So this, you could say this is a different vector. Yeah, that's not a set. Let's call this y. There's some, yeah. This is on the board, capital and little s's. Yeah.
You might have forgotten the empty set at the very end.
Yeah, that's true. Yeah, so yeah. You're right, yes. Or I could assume that f of the empty set, for simplicity, is 0. You're right. I should have done that. Or 1 minus the largest value and then use the empty set. Any other questions about the extension? Okay, so let's go back to the overview. So we have our extension, we have the convex relaxation. How to optimize it? There's various different ways. You can use convex optimization methods. You can actually also use combinatorial optimization. So there's also combinatorial optimization methods, which was essentially motivated by the fact that, say, minimum cut or so are special cases of submodular minimization, and we have good combinatorial algorithms for them. Is there combinatorial algorithm for this problem? So I'm writing these here. These are actually combinatorial methods. Why am I writing them here? Essentially, you can view them as optimizing the convex dual of this problem. So what is going to be the convex dual of this problem? It's going to be convex minimization over convex set. It's going to be concave maximization over some convex set. So the convex set that we have here is the base polytope that they optimize over. So it's a some more complex thing, and we have some non-smooth convex function, concave function, simple function we are optimizing. That function is essentially, we want to maximize the coordinate-wise maximum between 0 and si. So basically, we want as few negative entries in our vector as possible. So now, so far, so good. The only complication here is that this set is easy to do linear optimization over, but anything else like testing membership in the set, doing a projection on the set, or any such thing corresponds to solving a submodular minimization problem. So all of these are things that we want to avoid. That's like a chicken and egg problem.
You need min. Max of means.
Yes. Yeah, otherwise it won't be concave. So how do you move in this polytope? That's the key question, because the function is easy, but the key question is how do you move in this polytope and stay in it without ever testing membership? So what these algorithms do is they essentially use network flow algorithms to make sure they still satisfy the constraints, and they move in this polytope, and they essentially move or remove as much negative mass as possible from the vectors. So there's a very, very high level intuition of what these combinatorial algorithms do. There's a lot more ideas behind this than what I'm super simplifying here, but the main idea is that you use network flow strategies to move in this polytope without ever testing membership. That's essentially what they do. So this is how this relates to actually this problem. It's like solving the dual with a combinatorial method. And then if you want strongly polynomial time algorithms, you can also do a combination of convex and combinatorial. And there's some more recent results, and maybe Aaron will tell you later this afternoon about their approach, their improvement. You won't? Okay. Anyways, it was your work, so yeah.
Happy to chat about it later, though.
Okay, yeah. So basically, improvements to cutting plane methods lead to further improvements in the best running times.
So what are T and M?
M is the maximum function value, and T is the time to evaluate the function. Okay, and of course you can think of other ways to do it. This is sort of a brief overview. So you see this actually is a very interesting, things you can do. One other question is, how far does this relaxation go? And let me show you one positive and one negative result. So one interesting positive result is that relaxation is actually quite rich, in the sense that I can even make it strongly convex and I can still read out the optimal solution. So what I can do is, I can say this piecewise linear function doesn't have such good optimization properties. Maybe I want this to be strongly convex, so I'm adding a strongly convex separable function to it. I'm removing the constraints and I'm minimizing this. You can generalize this definition to more than the hypercube. It's not obvious that you would see the discrete optimal solution from the optimal solution of this. Obviously, this has a different optimal solution from this one, because I can make actually that factor arbitrarily large. But still, you can actually do optimal rounding for this one. And the key insight here is that all we really need is, again, these level sets. So all we really need here is which entries are positive. And that's actually the same question that we have over here, which entries are positive, and these are actually the same. And it's stable up to this. And the other interesting thing is now we can again look at the convex dual. The convex dual is a weird geometric problem. It finds essentially the projection of 0 onto my base polytope, where it finds the point with the smallest norm on the base polytope. And this optimization problem leads to what's called the minimum norm point algorithm, or the Fujishige-Wolfe algorithm, by applying a specific variant of the Frank-Wolfe method, or the Wolf's method essentially, to solving this problem, finding the minimum norm point in a polytope. Yes?
Sorry, how do you define f outside the 0, 1?
Oh, essentially you can go by this sorting definition.
Okay.
And you just, this sorting like if you just say you have this definition with the sorting, or the definition with the pointwise maximum of these linear functions, that extends. So you can no longer easily interpret it as an expectation, but this max over linear function extends.
But wait, but the minimum still will be in this feasible region?
No, the minimum of this guy most likely will have negative entries. So you no longer have here a feasible region. It doesn't matter, because you can extend that definition.
Yeah, but how do you go back to, like, I give you this minimum, and how do you go?
And you take all the entries that have positive values, or no, negative actually works in this case. Okay. And you can prove that's optimal. The reason this is actually optimal is because this problem solves a richer set of problems. It solves what's called parametric minimization, which means minimize f of s plus alpha times cardinality of s for all alphas. And you can read out these solutions from basically the level sets of that thing. So without the penalty alpha equals 0, you'll get the optimal solution. So this is just a curious connection. This is the same as why you can do, for example, parametric max flow so efficiently. This is same underlying ideas, essentially. So just to mention this, this leads us to another sort of class of algorithms for solving problems like this, or doing parallelization and so on. I said I'll show you also negative results. So one thing where all of this framework breaks is if I say, I don't want to optimize over the hypercube, but I have more constraints. I want sets of size at most k. So, or some other constraints on my set. All of these problems essentially become not only NP hard, they become even hard to approximate. Basically polynomial lower bounds on the approximation factors for pretty much all of these problems of constraint submodular minimization. And in that case, I cannot get a tight convex relaxation anymore. I can do this, I can use it as a relaxation and then try to do rounding, but it's no longer going to give me the exact optimal. So, but at least up to here, it's a pretty useful and nice framework, and actually this is a very efficient algorithm in practice, in general. Okay, so I have a little bit more time. I wanted to show you some other ideas. So let me show you a little bit about submodular maximization. I talked a lot about minimizing submodular functions. Let me talk a little bit about maximization. So for maximization, that problem already in itself is NP hard, so we cannot expect to get anything exact out of it. So think of max cover, max cut. These are instances of submodular maximization problems and obviously not solvable exactly in polytime. still we can hope to get approximations, and actually in most cases we can get very good constant factor approximations. Here we have to make essentially some distinction. So here we have to care about, say, if the function is non-negative. Here, let's assume it's non-negative. And there's another distinction, that is the function monotone increasing, meaning as my set grows, the function value only increases, or can the function be arbitrary? So coverage function would be increasing. A cut function can be decreasing as well. So for maximization, if I call these simple cases. Basically, I have a monotone function. I have a constraint. I don't want to pick more than k. A simple discrete greedy algorithm actually gives me the theoretical optimum, which means a 1 minus 1 over e approximation. So algorithm is very simple. I start with the empty set. I pick the best item by its value, and then I pick the best augmentation, etc., until I have k. So super simple algorithm. It gives me 1 minus 1 over e. And the key idea in proving this is to show that in every iteration, you close the gap to the optimum by a certain factor that depends on 1 over k. But then if you talk about more complex constraints, or you talk about non-monotone optimization, this algorithm is no longer optimal. And in that case is when we may care about doing continuous extensions and relaxations. And that can give you the optimal factor. So again, we have the same idea. We have our discrete function defined over sets or binary vectors, and we want to find some kind of interpolation that we will optimize and then somehow try to do some rounding. Now, we have our Lovász extension, which is convex, but if we want to do maximization, that may not be the right thing. Convex maximization is not a very easy thing to do. Can we do something else? So you could think about, well, I could take, like, maybe this is the convex envelope. I could take the concave envelope. It exists, but unfortunately, it's very hard to compute it. So it's not tractable. So we have to find something else. And that something else will actually be what we saw in the beginning, this independent joint distribution. So as I showed you already in the picture, this thing is not a concave function. But it'll turn out that it has good enough properties that you can say something non-trivial about it. And this something that is non-trivial about it is actually the same that the greedy algorithm hinges upon, and that is diminishing returns. We don't have concavity, but we have diminishing returns, and that takes us quite a long way. So what diminishing returns means is that if I now look at this continuous function, I take the second derivatives, the Hessian is basically all negative, all non-positive. And the implications that this have is that this function is concave in increasing direction. So if I start at 0 and I go in directions where my entries increase, you see this looks like kind of concave. And if I go in directions that are swapped, so basically increasing one coordinate and decreasing the other, that's like this direction. You see it looks concave, and it actually is. You can prove that. Follows from this. It's not very hard to prove it. So this is actually two very important properties. So what are we going to do? We are going to use this, and we are going to try and maximize it as well as we can. And in fact, this is going to be a continuous non-convex maximization, because not non-concave, essentially. And then that's not going to give us the optimum, but it's going to get us, in the case, for example, for metrics, in a constant factor of 1 minus 1 over e, and then we are going to do lossless rounding. How do we do rounding? For rounding, let's say we have found some point here. We are going to use these convex directions. So if you think of a constraint that says, well, maybe xi and xj have to sum up to something smaller than a certain budget, you cannot arbitrarily increase both of them if they already sum up to that. So you have to increase one and decrease the other. So you find two of them, increase one and decrease the other. And now if you think about it, it's concave, a convex function in this direction along a line. So if you have a convex function, you're at some point, there's always one of the directions your function is going to increase. So you can always find one direction along your line of increasing one and decreasing the other that you're going to improve the function value. And that's the idea behind the rounding here. So that's actually a very important property. There was a question?
Yeah, so if you have 3 coordinates, then what is, like, if you increase 2 2 corners and decrease 1 instead?
So, yeah, you could do it, but then you don't know. So the way you do the rounding is you only ever do 2 at a time. Yeah. And same actually works also for non-monotone, where there's actually interesting correspondence between randomized greedy and continuous optimization algorithm. So how does this continuous optimization work? Let me just show you one example, which is in the case when your function is monotone and the constraint is what's called a matroid constraint. Think of in the simplest case as like still a budget constraint. Like they should all sum up to something smaller than k. That's a very simple example. So we have some polytope over which you can optimize. And now what this so-called continuous greedy algorithm actually is doing is like Lorenzo talked about the Frank-Wolfe method. It's essentially an instance of a non-convex Frank-Wolfe method. So how does it work? Is you start at 0 like the greedy algorithm, and now in every iteration it finds a good direction to go. And that good direction to go should better stay in your polytope, in your feasible set. So how do you ensure this? You find the direction or the corner of your feasible polytope that's most aligned with the gradient. Gradient itself, you don't know how far you can go until you go out of your constraint set. That's not so good. So you find the guy that's most aligned with the gradient, that's sort of the best corner to which you can go. And then you go a little bit into the direction of that corner. And if you set these correctly, you're actually going to get always a convex combination of corners, and you're going to be inside the polytope all the time. That's the idea. So this is actually exactly the same as the Frank-Wolfe method, with a special twist of how you combine the points, and that you have to start at 0 in this particular case. Yeah?
Shouldn't you have 1 minus alpha multiplied z?
Yeah. So this is a different from the usual convex optimization Frank-Wolfe, but it's conceptually very close. And in fact, the original paper didn't prove it that way. They used a differential equation and discretized it. But if you discretize it, this is essentially what comes out.
Because it's not clear to me why you stay in the polytope.
Oh yeah, I will argue it depends how you set the alpha. Essentially, the idea here is that you start at 0, and you set actually alpha to 1 over capital T. So in the end, you have taken T steps, and in each step, you take a corner, and you add it with fraction 1 over T. You do that T times, you get a convex combination. Yeah, but it depends how you set alpha. OK, so why is this good? So let me show you the analogy with the analysis of the Frank-Wolfe method. So this is the proof from my lecture notes when I first talked about Frank-Wolfe and then about this method. So here's the idea. First thing you do is Taylor approximation. This is the standard proof of first order Frank-Wolfe optimization. So progress I make in each step. So basically by going to step T plus 1, I'm at lower bounded by the previous point plus the gradient times the direction I went into plus some second order terms. This is just a Taylor approximation. So now what you typically do is now you use this and you use convexity and you show that this indeed tells you that you're making sufficient progress and you get the standard 1 over T rate. So here we don't have convexity, but what we have is diminishing returns, which gives you actually concavity in the positive directions. And showing this, what they showed in the paper is that what you can show is that there is a point where the inner product gives you that this inner product is upper bounded by opt minus your current point. So basically the current gap. So, and we know that when we are doing the argmax here, we are actually finding the best possible point. So we are certainly at least as good as this, because we're finding the argmax. So we can just plug it in here. It's just replacing that inequality up there that we got from diminishing returns. And once you have this, you rearrange it, and what you see is that what this actually shows you is that just with a greedy method, in every iteration, you close the gap to the optimum by a certain factor, 1 minus alpha. And if you just now iterate this and set alpha to 1 over T, you get this. And this T goes to infinity, this is going to be 1 minus 1 over E. And this is going to go to 0. So this is essentially, in a nutshell, how you can show that this non-convex Frank-Wolfe algorithm still gives you a very decent approximation. In fact, this is optimal. In this case, 1 minus 1 over E. And then you do rounding. So let me just, with that, sort of close that part and give you like the overview. What we saw is that we can take this submodular optimization problem, the discrete problem, can take different types of relaxations depending if you want to do maximization or minimization, and get exact or very good constant factor approximations out of these relaxations by carefully using the properties. And the key insight is use convexity relaxations if you want to do minimization, use diminishing returns if you want to do maximization. So now I'm almost out of time, so let me just sketch one more idea here, and that is how do these ideas generalize to functions beyond sets? So how does submodularity generalize to functions beyond sets? Well, I already said you can view sets as binary vectors. And in fact, instead of binary vectors, you could take integer vectors or real vectors or something. So in that case, that same inequality becomes just a lattice conditions where you take coordinate-wise maximum and coordinate-wise minimum. And it's exactly the same definition. The question is, what kinds of functions satisfy this? If I look at continuous functions, if I look at other discrete functions, what kind of functions are functions that satisfy this kind of inequality? And for a bit more understanding, if the function is differentiable, this is what it corresponds to. That if you look at the Hessian of the function, all the off-diagonals are non-positive. But that also means this is actually not, it says nothing whether the Hessian is definite in any way. And in fact, these functions can be convex or concave or neither. So here's an example of such a function. So it contains convex functions, concave functions, and non-convex functions, essentially. So the key question is, do the results that I talked about, do they generalize in any ways to these kinds of functions? And in a nutshell, they do, to a certain extent. If you want to do maximization, we realized all we need is diminishing returns. Remember, that's like what gave you the concavity and so on. Diminishing returns is not the same as submodularity in this general case. It's slightly stronger, but if you have it, so essentially if you think about this negative Hessian condition, all of the entries of the Hessian have to be negative. And then it works. And in that case, you can pretty much generalize, most of the maximization results. In particular, this continuous greedy method that I said actually just relied on this condition of the multilinear extension.
So, sorry, what do you mean here? That there's some constant approximation factor or? Yes,
so you get an approximation factor. Like basically the same kinds of approximation factor results out.
That depends only on n, on the number of values.
The approximation factor was constant, didn't depend on the dimension. Yeah. In that case, not. For minimization, the picture, you cannot do exact continuous optimization, at least I don't know of anything, but you can discretize it, and once you have discretized it, you can actually use all the ideas from discrete optimization. For example, you can generalize the Lovász extension to this case. With a bit more effort, it's going to become more complex distribution. The coupling is done via optimal transport, but essentially you get a convex extension out, and you can do exact optimization for that convex extension. You can also do a reduction to the set functions in certain cases. So many of the ideas generalize the convexity and concavity ideas. So you can, in some cases, also use now discrete optimization to solve continuous non-convex optimization problems. That's when this is most useful. Let me just skip this, and it has certain applications in robust, mostly in robust non-convex optimization and learning problems. Okay. That's sort of just to show you a little bit that it can also go the other way around, that the ideas are actually more general. I will skip this part. I wanted to just mention there's also other interesting connections of submodularity, negative dependence, and the theory of real stable polynomials, but we have lots of experts here. There's Nima, there's Nishit, and there's Nikhil and Shayan also, so these are good people to talk to about these things. So let me just jump to the conclusion. That's this. Okay, so what I showed you was a little bit of sort of one topic of connections between discrete and continuous optimization, how you can use convex and concave aspects both of a certain class of discrete optimization problems to get good relaxations and good approximation algorithms or exact optimization algorithms out. And moreover, even up to certain non-convex optimization problems that you can solve with the same ideas. With that, thanks for your listening, and I'll be available for questions in the break also.
We have time for one short question.
So this is only in the black box model, right? I mean, the only access to your function
yes.
that you have is if there's, if you have a representation of your function
yes.
in some way, it comes from, whatever. Do any of these results get sharpened, or
so in
how does representation actually help?
Okay, so what in certain cases you can get better results. So for example, in the convex case, you can get faster optimization. So if you think about like the minimum cut problem, you actually have the graph. You can even get a polynomial time algorithm. If you have, say, something that looks like a sum of functions, of easier functions, you can use this, can get better, faster algorithms out by using actually that decomposition structure, for example. So in that case, it leads to faster algorithms. In the maximization case, you can sometimes get better approximation algorithms. If you think of the max cut problem, it's better approximable than a half, which is the lower bound for like black box general submodular maximization. So you essentially can use more of the structure of the problem to get better optimization, faster optimization, or better approximation results, essentially. Yes.
Okay, thank you.